Go for it. Go for it.
Oh, I don't know.
Oh, okay, bummer.
Sorely lacking.
Yeah. Okay, oh, there's more folks coming in. Good. Okay. Good afternoon, everyone, and welcome to the 215 press conference at the 225th American Astronomical Society meeting on the topic of the Milky Way and the local group. My name is Inge. I am one of the deputy press officers for the Society. The press officer, Rick Feinberg, is in the back monitoring the web, and deputy press officer Larry Marshall is over there and will help us with the microphones. Welcome, everyone, here in person as well as virtually on the web. First of all, I would like everyone to do the usual, whatever you do when you go to the movies. Please turn off everything that makes noise. Phones, I don't know if anybody still has pagers, whatever. Those sorts of gadgets. And because we have folks virtually listening through the webcast, we will have, well, first of all, everyone speaking in order, after which we take questions. If you have a question or if you answer a question, please always speak into the microphone. Otherwise, the folks on the web can't hear you. For the presenters, when you want to refer to something specific on your slides, use words or use the mouse or the cursor. Do not use lasers. Again, the web folks can't see it. For anyone on the web, please ask your questions via the web chat. So today's topic is the Milky Way and the local group. First, Daryl Haggard from Amherst College will introduce Chandra and VLA Galactic Center campaigns targeting the center of our galaxy, Sagittarius A and G2. And we'll find out what mysterious things are going on in the center. Next, Andrew Fox from the Space Telescope Science Institute will talk about Hubble clocking the high-velocity outflow from the Milky Way's core. So again, interesting things that are going on in the center of our galaxy. Paul Scowen from Arizona State University will talk about new Hubble Space Telescope images of the Eagle Nebula. You all remember the fantastic Eagle Nebula image, the Pillars of Creation, that made the rounds some time ago. Now there is a beautiful new one, and he will tell us all about it. Then David Nidever from the University of Michigan will talk about the first results from the survey of the MAgellanic stellar history, otherwise called SMASH, which will be smashing, I'm sure. And finally, Julianne Dalcanton from the University of Washington will talk about highlights from the Panchromatic Hubble Andromeda Treasury survey and tell us all about Andromeda. And with that, I will turn it over to Daryl. You all know how to do this, right?
It's just the same button.
Yep, and then you look for yours.
Great. All right. Thank you, everybody, for being here. This is like the quietest press room I've ever seen in my life. So I'm going to be talking to you today about, I gave it a slightly cuter name, the Milky Way's massive black hole lashes out. The black hole's been getting a lot of competition, so I'm going to be talking less about G2 and more about Sagittarius A star, the supermassive black hole in the galactic center today. And this is indeed a summary of very large campaigns that I've been participating in with Chandra and the Very Large Array. and I have my contact info up there. So just to get us oriented, I'm going to start actually fairly zoomed into the galactic center. I think we're walking out as we move along the table here, so you'll see further and further zoomed out images. This is a beautiful multicolor image from some of our orbiting observatories, Chandra, Hubble, and Spitzer. Sagittarius A star, I actually have a little thing, is located in this cluster of young stars, which looks very blue, kind of a blue cluster in the image you're looking out here. We know there's a massive black hole there. The black hole has slightly more than 4 million times the mass of our sun, and that's what earns it the superlative supermassive. And we know about this black hole from a lot of different lines of reasoning. Some of the most impressive comes from imaging of stars actually in orbit around what might appear to be empty space, but we can tell is a very massive, massive object living there. So beautiful constraints on the mass of this black hole, despite it being extremely far away. So this is a nice zoom-in picture. The supermassive black hole is in the direction of the constellation Sagittarius. So we're in the southern hemisphere, zooming in, switching from optical to infrared imaging. And I'm going to start by talking about some of the competition. First, there's this little gas cloud. And so for anybody who's been following what's been going on in the galactic center, this gas cloud is called G2. And G2 appeared to be making a beeline for the supermassive black hole. There's been a huge amount of debate. Is it a gas cloud? Is it a star? What's happening with G2? I'm going to be a representative of the X-ray astronomy community today. And from our perspective, nothing happened. We never saw G2. There was no bow shock. There was nothing. There were none of the fireworks we had hoped to see in the X-ray. So this is Sagittarius A star's #1 annoying distractor. Here comes annoying distractor #2. So as we were watching and looking for this little gas cloud to come along and interact with our supermassive black hole, a magnetar went off. So I'd love to point to this really bright source here on the screen. My mouse isn't really working, but you can see the bright source. I'd love to tell you that was our supermassive black hole, but it is indeed not. It is one of fewer than 30 known magnetic pulsars that went into outburst right on top of my source. Very annoying when you're trying to watch for very low surface brightness changes. But there are only 30 of these known in our galaxy, and they're incredibly cool and exotic. And it is a neutron star in orbit around a supermassive black hole, likely associated with a disk of stars that's in orbit around the supermassive black hole. And so what you're looking at here is actually an X-ray image. You'll notice that it's a very photon-starved regime. X-ray astronomers come to know and love each one of our photons. We could almost name them. We know when they hit the detector. We know how much energy they had. So this is very different than you might be used to seeing in optical or infrared astronomy, where you're really flooded by a bath of photons. These are really particular photons. We can literally almost count every single one. The magnetar is quite bright, so we had a few little issues to do with that. But so Sagittarius A star had just about enough of this competition. And so early last year, it could stomach no more, and it let out its brightest flare ever in the history of our observations of Sagittarius A star. So that's what you're seeing in this little blue inset. This is an image from buried way down in the interior of our galaxy. And the blue persistent source you see right now, that's the magnetar. And then the very, very bright outburst is actually a flare coming from the inner regions of the accretion flow around the supermassive black hole. So this is the brightest flare we've ever seen from Sagittarius A star, and indeed I think it was the supermassive black hole reclaiming its stake on coolness in the galactic center. So I'm going to march through a couple of slightly more technical slides here just to show you what this looks like. So this is what we call a light curve. We're just looking at photons or counts that come in and hit the detector as a function of time. My time axis is really long here. I'm going from April through October, April 2013 through October of 2014. So as not to mislead you, the Chandra X-ray Observatory did not work in my service for an entire year and a half straight. They would never give me the telescope for that long, though it would be awesome. There are actually gaps between a whole bunch of these observations. They're not continuous in time, but I've pulled the gaps out so we can see the data all together. So this low-level flickering is characteristic of Sagittarius A star, and that first spike you're seeing there is that very, very bright flare I showed you the movie of. This flare flare is 400 times the quiescent level. And in fact, some of the people working with me on these X-ray campaigns argue the quiescent level is even lower than that because we have lots of little flickering flares. And this flare may be, in fact, be another factor of 10 brighter than quiescent, so perhaps as bright as 4,000 times over the quiescent, regular, calmer accretion flow onto the supermassive black hole. We caught a second very bright flare, so this is the brightest one we've ever seen. This is the second brightest one we've ever seen. It was around 200 times quiescence just this last October. And the previous record holder was around 140 times the quiescent level. That was published by Mike Novak a few years ago. So these bright flares are really exciting. And we had to do a few adjustments to our instrument configuration. And we had this exquisite precision from the Chandra X-ray Observatory. And we were counting our photons with great accuracy. And we could actually take this flare and kind of break it down into its individual components a little more. You see it's actually got two peaks. It's not a single coherent flare. It's slightly asymmetric. And I'm just going to flash up a few text things, but the point I would like to make with the text that's written on here is just to say we do not think that these flares are connected to the G2 object. This is not pieces of G2 being pulled off. And the reason for that is that the timescales don't quite match. The time scale for these flares is fairly rapid, thousands of seconds, something of order an hour or two, which is really characteristic for objects that are something like 1 AU, so roughly something like the Sun-Earth distance. G2's closest encounter is 150 AU, so the time scale doesn't actually match up for the G2 object, at least not at this particular point in time. Okay, so this is the brightest one. This is just a plot to say ours is off the charts. And this is a slight zoom in just to show you there's some asymmetry and sort of passive additional flares with this second bright flare in October. The other cool thing is, so this is what I was talking about. We're really counting individual photons here. And one thing we got really excited about was seeing if we could see little sub-flare variability. That doesn't maybe sound super cool, but if we could do that, we might be able to pin down the position in the accretion flow that these flares are coming from and say how close to the supermassive black hole the flare originates. And getting in and seeing the inner part of the accretion disk around a supermassive black hole is pretty awesome. So it turns out that the statistics in the intra-flare variability were not as good as we had hoped. I'll just walk through a few of the time scales and then talk just quickly about our models. So 6 kiloseconds, that big bump you see there, is the characteristic total time scale for the flare. The 2 kiloseconds is the distance between the two peaks. I showed you it had two peaks in it. And then after that, there's a whole bunch of sort of other little flickering, and that's what we were hoping would have a strong signal, but it's still pretty close to our noise, so we couldn't confidently detect a sub-flare variability that would place it right next to what we call the innermost stable orbit. And just to say why we'd care about that, if you could actually pin down that the position of the flare and place it near the innermost stable orbit, you might have an opportunity to distinguish between a spinning and a non-spinning black hole. So this is something that we might be able to work on in the future if we can get bright flares with this really exquisite timing signature in the X-ray. Okay, so why the tantrum? So I've tried to kind of frame this as Sagittarius A star getting irritated by its loss of press in recent years. But really what we want to know is what's causing the flares. That would be the question that we're seeking to answer. There are two sort of leading theories. I don't know if I'll be able to get my little movie to start here. So this is the sun displaying some of its own flaring events. These are magnetic reconnection events where the magnetic fields actually reconfigure, and as they do that, because they've been pushed too tightly together, they let out extremely energetic bursts of energy. So a phenomenon similar to this might be happening in the inner regions of Sagittarius A star's accretion flow. Another possible explanation might be that you're actually disrupting small rocky bodies inside the accretion flow. Here's an asteroid being torn apart in the inner region of Sagittarius A star's accretion flow, and as that disruption happens, it flares up and then dies back down. So the skeptical among you should be looking at this and saying, you've got to be kidding me. Your two models are magnetic reconnection, like something that happens on the sun, or asteroids being shredded apart. Like, you can't do better than that, and the answer is not yet. This is an unsolved mystery. We really don't know. We have beautiful data. We've been trying to hammer at this question for a long time, but we don't quite yet have the multi-wavelength, simultaneous data that we need to nail down the physical mechanism and actually distinguish between these two vastly different models. And so this is a big discovery space, and these extremely bright flares might be one of the keys for getting in there and really starting to understand what the inner parts of this accretion flow looks like and what these flares, where they're coming from, what they are. I think that's it.
Thank you, Daryl.
Okay, good afternoon. I'm Andrew Fox from the Space Telescope Science Institute in Baltimore. The title of my briefing is Hubble Clocks the High-Velocity Outflow from the Milky Way's Core. So we're going to continue the discussion on recent results from the Galactic Center. What we've done in this project, which has recently been published, is that we've measured for the first time the velocity of the gas that is gushing out from the Galactic Center and into the halo of the galaxy. To set the stage for the science, a few years ago, NASA's Fermi Gamma Ray Observatory made a new discovery. What Fermi found was that above and below the galactic center, there are two giant lobes of plasma, of ionized gas. And these extend about 30,000 light years, both above and below the center of the Milky Way. You can see them here in this all-sky map taken in gamma ray emission. This was a new component of the galaxy that had not been discovered until then. It's also been realized that these so-called Fermi bubbles emit radiation in other parts of the spectrum, including microwave radiation. This is some microwave data from earlier that actually shows a very similar morphology, a similar shape as the gamma ray emission. You can see above and below the center of the galaxy, we see these balloon-shaped structures that are glowing in emission. If you look in radio waves, you find a very similar picture as well. So what we have been doing recently with the Hubble telescope is designing an experiment to study the properties of these Fermi bubbles using a technique called spectroscopy. So we study quasars, bright objects that happen to lie in the background, and using the lines of sight to those quasars, we can intersect the Fermi bubbles. And the gas in the Fermi bubble leaves a unique signature in the spectrum of the quasar that we can analyze and use that to determine important information about what's happening in the Fermi bubble. So I'm going to show you one slide where I give you an idea of the sort of data we actually work with from Hubble when it comes to spectroscopy. This is the so-called absorption line where I'm showing you how much light there is as a function of color, which is the same as saying how much light is there as a function of velocity. This is a spectrum of a line of silicon, some silicon atoms. And what we're able to say when we look at this is that in this line of sight towards this quasar, we see gas moving towards us and gas moving away from us. And that is exactly the signature you get when you have a sight line that passes through an outflow of material coming out from the center of the galaxy. So we have what we think is a biconical outflow in which the near side of the gas is moving towards us, the far side of the gas is moving away from us. And using spectroscopy, we can see the signature of those movements, so-called blue shifts and red shifts in the data. So not only can we measure that, we can also say something about the elemental composition in the wind. And in particular, we've detected silicon and carbon and aluminium in an electrically charged form. So we're saying something about what chemicals are in this outflow, as well as the fact that it's very energetic. So to put those results onto one slide, here is a graphic that is coming out today as part of a NASA press release on this story, where we've color-coded the different sides of the Fermi bubble according to whether the gas is moving towards us and away from us. And on the inset panel at the lower left there, you can see a graphic showing how on one side of the spectrum we see the blue-shifted absorption, on the other side we see the red-shifted. And this is the first time that we've seen that unique signature in a single spectrum. So what are some of the science consequences of this? Well, the first thing we want to focus on is that the velocity of the outflow that these data imply is about 900 or 1,000 kilometers per second. So in more familiar units, that's 2 million miles per hour. So that's the speed at which this gas is gushing out from the center of the Milky Way. Once we have a speed, and we also know how far away from the center of the galaxy this gas has got to, we can determine its age. How long has it taken the gas to get to that point? And when we do that calculation, we find it's between 2.5 and 4 million years. What that means is a few million years ago, there was a very energetic event close to the galactic center, and we're seeing the remnant of that event where the gas has been blown up into the halo and is now venting up into the Fermi bubbles. And what's interesting is that theoretical estimates for how old the Fermi bubbles are were also of order of a few million years. So we're finding a number that is very similar to what was predicted by theory for the age of the Fermi bubbles. Now, there are still open questions. In particular, what is driving the wind and causing it to be launched into the halo is still an ongoing mystery. The two main explanations for this are whether you had a burst of star formation and supernovae close to the galactic center that drove the gas out, or alternatively, is it something to do with a supermassive black hole? The supermassive black hole can also accrete gas onto its surroundings, and that gas can then be blown out into the Fermi bubble. So what we're doing is we're enlarging our sample. Instead of just looking at this single line of sight, we're going to be looking at more directions and looking for trends to see if the gas is slowing down or if it's accelerating as it moves away from the core. This paper is online at the following website address. There's a NASA press release out today, and my contact details are on this slide. Thank you.
Okay, good afternoon. I am privileged to be able to present to you today some new pictures that have been taken of an old friend. You may remember some 20 years ago, which is a little alarming, that we went and took the first pictures at Hubble resolution within a year or two of its repair of the Eagle Nebula. It was a remarkable set of data that allowed us to look at the issues of how star birth and planetary system formation in the close proximity of massive stars allowed you to see how the nascent environment, the environment in which those stars and planets formed, could ultimately be affected by the proximity to those stars and the strong winds and the intense ultraviolet radiation that came from them. This particular picture became rather popular and has shown up all over the place, including several movies and all kinds of stuff. And today we get to present to you some new pictures that have been taken with the WIF3 camera on HST. And with no further ado, we'll move on to the picture itself, and there are some better versions that are closer in. I'll show you in a minute. But this is how it compares to the original picture. We have, as you can see, a wider field of view with the WIF3 data. With the same exposure times here, we are going about a factor of 10 deeper. And so what this, the immediate question is, why on earth are you doing this? Why are you taking another picture of this thing? And what it actually allows you to demonstrate is how far Hubble has come in its 25 years of service to the astronomical community. The telescope itself, the glass has not changed. What you're looking at is the advances in the instrumentation that has been put on the back end through servicing, as the original design for Hubble had always called out for. We get to look a lot closer with the WIF3 camera. We have a factor of 2 improvement in resolution over the original WIF-PIC2 data, and it really is quite remarkable. So let me get into a few of the details about what we can see in the middle of this thing. So here, and there's one more, of course, important footnote, that while you're looking here at the same kinds of optical data, remember that the color separation that you see in these pictures actually represents physics, right? The blue is doubly ionized oxygen, the green is ionized hydrogen, and the red is singly ionized sulfur. And that maps to energetics. It maps to how energetic the photons were, what the density of the gas from which that bright emission is coming from is telling you. And so the insight that you get from these data remains as good, but the fact that you've now got twice the resolution allows you to be able to go in there. And what we did 20 years ago was we did the best we could with numerical analysis to try and model how the gas dynamics at the very interface, at the walls or the tops of those pillars that you see in this picture was working. But now we've got an even better estimate about how sharp that interface is, and it really is quite remarkable. But the added extra that we now have with free is the ability to look in the infrared. And so the picture that goes along with this one is this one. And what you can see immediately there is there's an awful lot more stars. And the reason for that, of course, is that in the infrared, you get to see through the intervening gas and dust that is endemic to an H2 region or a massive star-forming region of this kind. And you get to look through and see so many new stars back in the wall of the cavity that is an H2 region. But what you see also is that the pillars themselves become quite transparent at infrared wavelengths, but not completely. The reason that those pillars exist, I may remind you from the work we did 20 years ago, is that the clouds at the top of each pillar are actually quite denser than the environment around them. And the reason that these pillars exist at all is because the massive stars at the very center of the cluster of the Eagle Nebula are doing an awful lot of collateral damage. Their strong stellar winds and ultraviolet radiation are blowing away all the gas and dust they can get their hands on. But these pillars persist because those 2 or 3 clouds of denser material at the top of each pillar are actually shadowing the gas below them. And so that allows you to have them persist and provide this almost inside-out topology. This was actually the original reason we went after the Eagle, was because when you look into most H2 regions, they're very bowl-like, very cavity-like, and this turned the problem around. So you had fingers popping out of the cavity wall, and it allowed you to look at the problem in profile rather than trying to guess what the edge of the cavity was doing. And so it's a remarkable image. The immediate thing that comes to mind, or the questions that come to mind, is what does this show you that you didn't have access to before? And that is trying to look and see what's actually in the tops of the pillars, and so we'll come to that in just a second. So compared face-to-face or edge-to-edge, this is what the data looks like. A quick reminder about the scales involved here. The pillars are about 5 light years long. It takes light about 5 years to go from the top of those pillars to the bottom of those pillars. So they're quite appreciable. One of the things that we were very interested in 20 years ago was exactly how sharp the edges of those pillars was. And at that time with WIFPIG 2, it was pretty much at the limit of the resolution of the system. And the remarkable thing we can say today is that it's still at the limit of the resolution of the system, even though we've got a factor of 2 improvement. So we're looking at the edge of these pillars as being less than 100 astronomical units across in terms of the transition from what is the inside of the pillar to what is the gaseous interior of the nebula. And that's remarkable. And that really does place some actually very stringent constraints on the calculations that we might do and we intend to do to revisit what the gas dynamics of the system look like. So when you zoom into the top of the most prominent pillar on the left-hand side, you of course see these nodules or eggs or whatever your favorite name for these things is, but they are essentially protostellar systems that are being dug up too early. Remember what they're doing when you have a massive stellar environment like this go off in a gaseous molecular cloud. The very fact that you form stars in the particular heart of that cluster causes the gas around that cavity to get compressed, and you end up with secondary star formation going off. So within the boundary, within the dense boundary of this cluster, you expect to find the next generation of stars being formed. But what's going on here, what we had always suspected would be there, and we found in the evidence of this, is that the gas is being ablated away. You can see the streamers here in blue, where the material is being heated up by the ultraviolet radiation, then being ablated away by the strong stellar winds. And those horse head things sticking out of the top of the pillar are in fact dense globules of gas that are in the process of trying to contract down to stars that are being unfortunately dug up from their nursery before they were ready to come out for prime time. So that's something that was very interesting at the time. Now, when we compare this to the infrared picture, we have the opportunity to go in there and really look to see which of those nodules actually has a stellar source in the heart of it. And based on the estimates that we had about 20 years ago, we had estimated somewhere between 60 and 70 of these nodules existed. And I think based on what we can see in these pictures right now, and I've only been able to look at these for a few weeks, is that we see probably 5 to 10 of these objects that do appear to have a very definite infrared source in there. And so you can, that immediately follows on to the success rate of forming stars in this kind of a somewhat acidic environment for their success. And it allows us also to look at what that implies about how things evolve. Now, the other thing that this data gives you when you have a 20-year baseline is, has anything moved? And we are happy to report that a few things have moved. Down in the heart of that top pillar there are, as I just said, several protostellar systems. And what happens when you try to collapse that gas down is it does make a number of jets as the system tries to dump its angular momentum to allow successful accretion of material. And those jets can often be regarded as signposts pointing back to, we just made a star right here. And that's what we see here. We see this jet here at the... is there a cursor? There is a cursor. There we go. That there's a source down in here that has a jet wending its way up here, and we have seen that the very end of that jet, which wiggles around a bit as they do because they're not going through a completely homogeneous medium, has actually moved in the 20 years between the two data sets. And that's quite remarkable, and that allows us to have a look in there and really understand whether those motions are consistent with the kinds of stellar collapse we believe is going on, and in terms of gaseous collapse to form those stars. But it is a remarkable example of what Hubble has been able to do in its 25-year lifetime. And these data, there's a lot of data in there that I think we can revisit to go back to the science goals that we reported 20 years ago and look to see how things have changed and how much more insight we have now that we have the infrared, and now that we have twice the resolution, and now that we have a factor of 10 deeper images in the same exposure time. Thanks very much.
Hi, I'm David Nidever from the University of Michigan, and I'd like to present the first results from the survey of the Magellanic Stellar History, or SMASH. SMASH is a large collaboration of 30 astronomers to understand the structure and formation of our little neighbor galaxies, the Magellanic Clouds, that you can see here in this image. So one of the primary goals of modern astrophysics is to understand the origin and formation of galaxies. We have a general framework for how this works, as illustrated in this computer simulation. Under the attractive influence of gravity, smaller galaxies merge together to form large ones, and at later times, the larger galaxies eat the smaller ones, and this cannibalistic process produces or leaves remnants, shredded remnants, in the periphery of the large galaxies. We now have ample observational evidence of this cannibalistic growth process in large galaxies. We can see these streams of small shredded galaxies torn apart by the larger ones. But there are many more small galaxies than larger galaxies in the universe. The dwarf galaxies are the most common galaxies in the universe, as you can see in this picture of a computer simulation. What we'd like to know is if this cannibalistic growth process also happens on small scales and not just for large galaxies. Simulations have predicted that this should be going on, but there's little observational evidence of this. And that's because dwarf galaxies are difficult to study because they are intrinsically very faint, and most are far away. But luckily, there are two nearby dwarf galaxies that we can study in detail. That's the Magellanic Clouds, as you see here. The large and small Magellanic Clouds are the largest dwarf satellite galaxies of our own Milky Way galaxy and are quite nearby. In fact, they're so close that they cover a huge part of the sky, and it's actually made it quite challenging to map out their extended stellar structure. Now, most previous studies have focused on looking at the very central parts of the Magellanic Clouds that you can see here, but that's changing now. The 520 megapixel dark energy camera, or DECCAM, was recently installed on NOAA's Blanco 4-meter telescope in Chile. This amazing camera can take a picture of an incredibly large area of the sky, much larger than was previously possible. To demonstrate the amazing capability of DECCAM, here's a common optical image of the central part of the small Magellanic Cloud, with the size of the Moon shown for scale. And this is one single DECCAM image. It covers almost the entire main body of the small Magellanic Cloud. For comparison, it would take over 1,500 images from a Hubble Space Telescope to cover the same area. DECCAM's incredible size gives us the ability for the very first time to map out the very extended structures of the Magellanic Clouds. And that's the goal of the SMASH survey. Even though we're looking at the Magellanic Clouds, there are actually a lot of Milky Way stars in the foreground and very distant galaxies in the background that look like stars. In order for us to separate out the Magellanic stars we're interested in from these other objects, we use a technique where we measure the brightness and color of points in our images, like the one on the left, and put it on a diagram as you see on the right. The brighter objects are near the top, fainter ones near the bottom, bluer stars on the left, redder objects on the right. So most of the objects at the top of this diagram are actually Milky Way, foreground Milky Way stars. Many of the objects at the bottom are distant galaxies. But luckily for us, the Magellanic stars that we're interested in actually live in this region of the diagram, and we can pretty cleanly separate them out from the Milky Way and background galaxies. Now this technique is so powerful that we can actually detect Magellanic structures over 400,000 times fainter and more diffuse than the Milky Way band that you see on the sky, as you can see here. So in this nice image, we see the Magellanic Clouds with respect to the Milky Way. And this is our 180 SMASH fields that cover this region. It's an immense and huge area, but we actually expect to find Magellanic stars over almost this whole region. We're still actively collecting and analyzing our huge trove of data, but we already have some very interesting results. So we have detected large Magellanic Cloud stars out to a distance of 50,000 light years from its center, as illustrated by this arrow and circle. This means the galaxy is over 5 times larger and covers approximately 30 times more area than what you see there at the center. And the density of stars at this large distance is over 100,000 times fainter or more diffuse than at the center of the large Magellanic Cloud. While some previous work by some SMASH members suggested that the large Magellanic Cloud might be larger, we're now clearly demonstrated that it covers a huge and immense area. This result suggests that the Magellanic Clouds are surrounded by a rich and complex field of debris left over from their formation and interaction. But this is just the tip of the iceberg. We still don't understand or know the origin of these very distant stars. In the future, we will use all 180 SMASH fields to map out the complex, extended structure of the Magellanic Clouds and use that information to decipher how these 2 nearby dwarf galaxies grew and evolved into what we see today. Thank you.
Hi, my name is Julianne Dalcanton. I'm the principal investigator of the Panchromatic Hubble Andromeda Treasury survey, also known as FAT. And what this survey is, it's a large area UV optical near-infrared map of Andromeda. Now, what's the deal with Andromeda? Andromeda is a big, fat spiral galaxy, a lot like the Milky Way, possibly even more massive than the Milky Way. And it has the benefit that there are many ways it's much easier to see and study than the Milky Way. If you look on the right-hand side, the Milky Way stretches all throughout the sky, and the problem is we're in the middle of it. So it's like trying to study the United States but not leaving downtown Seattle. You just have to look in each direction and hope for the best. Whereas Andromeda, it's far enough away that we can view the whole thing at the same time, understand how the different components of the galaxy all work together. So it's a wonderful system to study. But the bummer is it's farther away. And the problem is that it's farther away, and so when you look at the galaxy with any instrument you have, it tends to look a little bit blurry. Just in the same way you look at a distant mountain, it's a little bit fuzzier than when it's right in front of your face. And that's the case certainly from the ground when the atmosphere of the Earth blurs the background images. But you can kind of make some gains if you look at it with the Hubble Space Telescope. The Hubble Space Telescope is above the Earth's atmosphere, and so the view is very, very, very sharp. And you can see that from the ground, things that were just somewhat indistinct blobs resolve into hundreds and thousands of individual stars. And so you can make much more precise measurements, and you can make more precise measurements of fainter and fainter things. But there is a problem with this. The problem is that even though Andromeda is far away, it's only relatively far away in kind of a, astronomy sense. And so it actually covers a fairly large area of the sky. The area that it covers is larger than the moon. And we think the moon looks pretty big, right? So the reason that this is a problem is that the field of view of the Hubble Space Telescope is not that big. So, David prepped this by talking about how many ridiculous numbers of observations it would take to cover the Magellanic Clouds. It's about an equally insanely bonkers number of observations to try to look at Andromeda. So this is a movie showing all of the images that were taken over the course of this project. And so this project took 39 months to acquire these observations. I mean, the Hubble Space Telescope did many other wonderful things during this time period, but it also did a lot of this. The end result is we have over close to 13,000 images in 414 distinct positions. And these are also taken in 3 different cameras, covering a wide range of wavelengths. So in the same way that Paul was talking about the value of the near infrared, we have observations in the near infrared. We also look at the ultraviolet, at some of the more high energy photons coming out of the galaxy. Today I'm going to be highlighting work that's been done primarily with the optical. Now, the thing that we are releasing with NASA and ESA as part of the 25th year celebration of the Hubble Space Telescope is this absolutely beautiful optical mosaic that pieces together about 3,700 of the optical images. Now, this was a remarkable piece of work. So first of all, not only is it pushing 4,000 individual optical images, you have to align them at the level of individual stars. So these are aligned to fraction, basically better than 1/10 of an arc second across a couple of degrees on the sky before you can produce this image. And so this was a lot of work by Ben Williams. Dustin Lang was heavily involved in the alignment. Cliff Johnson. And then to do the imaging, we did a wonderful collaboration with Robert Gendler, who's a well-known astrophotographer. And so he did a lot of the visualization in terms of trying to find the right colors for the display. We've also worked with Zolt Live and other people at Space Telescope in terms of putting together this wonderful image. And I'm sure some of you have seen it up on the 6th floor. And that's not even at the full resolution. The full image is 100,000 pixels in one direction, and I think it's 37,000 in the other direction. And so if you display that at 300 dpi, that's a lot of feet. Okay. So the total in this image, this is just zooming in on a little part of it, is about 16 days of exposure time in the optical. NASA and ESA have released this as a press release today, and I strongly encourage you to suffer the long download time in your hotel room tonight and look at the full res thing. There's zoomable versions of it. It's really pretty gratifying. And it's one of the things that's kind of challenging about this is many people, when this project was awarded, asked the completely rational question about why in the world would anybody get this much time to look at not even one whole galaxy, a fraction of a galaxy. And the reason, besides the fact that you add Hubble to anything and it becomes much more awesome, is that this isn't a project to study one galaxy. This is a project to study stars. So to date, Ben Williams has been running the photometry, and we have measurements of 117 million stars. And they're all stars that are at the same distance, whereas in the Milky Way, you see a star, you don't know whether it's a bright star far away or a faint star that's close. Whereas here, we know these are all at the same distance. Andromeda's been studied for centuries at this point. And so we know where many different things in Andromeda are. And so all these stars we see in their individual context. So while that image looks, wow, that's a pretty nice looking picture of Andromeda, the glory of it is being able to zoom in and look at it at this sub-arc second level to pick it apart into the individual constituent stars. So what can we gain from this? Well, before I go on, I just want to say that this is one of the Hubble Space Telescope multi-cycle treasuries, and this is meant to be a legacy data set that you will be seeing press releases that use this data hopefully over multiple decades. So I'm just going to give you a couple of science highlights of things that we've done just in the past year, but there will be more. So for example, we know a lot about where Andromeda is forming stars. Andromeda is a common target for other great observatories. So for example, these are observations from 2 other NASA great observatories, from Galax, that's mapped in the ultraviolet, and that highlights a lot of young star formation. And in the red, observations with the Spitzer Space Telescope, which highlights warm dust, and which is also associated with star formation. And so you can see that a lot of the star formation in Andromeda takes place in rings. That it is a spiral galaxy, but those spirals are either very tightly wound or are actually genuine rings, like dropping a stone in a pond. Okay, and we think that this kind of structure is a very transient thing. When we run simulations, you see these kinds of structures move and evolve throughout galaxies. So this is what we think is going on with Andromeda. But what we can actually do with this kind of data is we can actually start to ask the question this is what it's doing now, but what was it actually doing in the past? So there's a way that you can do this by analyzing the colors and the brightnesses of the stellar populations of all the stars that you see. And the point is that as you look in different parts of the galaxies, the colors and the brightnesses of the stars change. And you saw this in the movie, that there's some regions where the stars were very red, stars were very blue, different brightnesses. And we can disentangle that and model it and figure out the past star formation history as a function of position in the galaxy. So this is work that was led by Alexia Lewis, a grad student at University of Washington. She'll be presenting this in the Andromeda session on Thursday. So here's a map basically of where the stars are forming now. And this is a map of where the stars were forming about 500 million years ago. And if you look, that star-forming ring is just, it was still there 500 million years ago, and that's a long time in terms of sort of the characteristic timescales for this galaxy. And so this was really a surprise to us. And to this point, we don't actually have a great dynamical explanation about why that ring would have been sitting there for that long. And more than just making a map at an individual time point, Alexia has been able to construct movies to actually show where star formation has happened throughout this period from the present day back to 100 million years ago. So let me show you this. Okay. Yes, and it played. So if you look, that ring just continues to be there. Now, Anil Seth at this meeting has a poster where he analyzes the density of stars in that ring. And more than just the young stars, all the old stars are participating in this ring as well. It's an enhancement of about 40% of the density of stars in this region compared to everywhere else. So it's this long-lived dynamical thing that's just kind of sitting there for reasons we don't understand. Now, if you look at the inner and outer rings that you see, those you can see them varying in strength throughout this time period, which is the sort of behavior that we expected, whereas the stability of this ring is something that we currently do not yet understand, but I'm sure there will be papers coming. So more than just the individual stars that you see, there's a wide variety of things that you see in the galaxy. You see star-forming regions in great detail. You see dusty features, which I talked about earlier this morning in one of the molecular cloud sessions. You see globular clusters, and you see stellar clusters. Now, stellar clusters are particularly interesting because we think that the majority of star formation that takes place in molecular clouds, and as a result, the stars that are left behind are intrinsically clustered. And some fraction of these clusters are relatively long-lived, and you can actually detect them for some period of time. So these star clusters are tracers of the peaks of the star formation process in the past. And in general, with star clusters, they're kind of hard to find. There's no great automated way to do it. And so Anil Seth and Cliff Johnson, a graduate student at University of Washington, in collaboration with Chris Lintott and Rob Simpsons with the Zooniverse, have led a very large citizen science project called the Andromeda Project, which we basically used citizen scientists to find all the stellar clusters in the Andromeda survey. And this was a ridiculously successful enterprise. There were close to 2 million images that people looked at and drew circles around all the individual clusters. And then Cliff and Anil did all of the work to try to pull together and figure out how do we combine everybody's votes about where clusters are to produce this catalog. And basically they found about 2,700 clusters, which is more than 6 times the number of clusters that were actually known before we did this study, which means we're probing down to very, very, very low masses. It's very complete. It's very, very uniform in terms of how it's done. And this is a sample of a size and a quality that's never really been available before. These clusters are also being used to study the initial mass function of stars, and Dan Weiss is going to be presenting about that tomorrow, and Cliff is going to be presenting about his thesis work constructing this catalog and some of the analysis that he's been doing with this. So I'm just going to leave up, there's a lot more information available on the website, including a packet with all of the various fat-related talks and presentations, and then there's also a little fact sheet of various fat facts that you can download with impressive numbers. Thank you.
Thank you very much to all of our speakers. We will now go to question and answers. Again, please, if you ask a question, please identify yourself by name and affiliation and make sure to wait for the microphone. Yes, we have a question up here.
I have an energetics question for both Martin Rackler, freelance, for both Daryl and Andrew, if I may. How do the energetic differences between magnetic reconnection and breaking up asteroids around a supermassive black hole affect your flare? And there's energy in the flare. How does that match? And similarly with you, Andrew, the bubble, does that match? The energetics of that bubble and the velocities match like a supernova explosion or something much more major going on in the center? Just wondered what the energy levels were like, and if you could tell the difference.
To start with the flares, it turns out that you can, since we're modeling this and not actually observing individual asteroids, and so the size distribution of those asteroids going in and exactly what their kind of glancing angle might be can be tuned in a model, depending on the mass of the asteroid and its sort of size for shredding and how close an approach it makes to the supermassive black hole. You can get different flare strengths and energetics, and same goes with magnetic reconnection. We see these in the most detail on the sun. Whether or not the sun is an appropriate analog for an accretion flow onto a supermassive black hole is a very wide open question. But we do have beautiful models of our sun, and we do know how to look at those magnetic reconnection events. They occur across a wide range of energies. They have cyclical patterns, and so the flares tend to be around 10 to the bright one was around 10 to the 39 ergs. That was the total amount of energy in it. It's pretty energetic, but it's easy to get that much energy out of either the tidal disruption of an asteroid or out of a magnetic reconnection event. And so we, as yet, can't use just the energetics to tell the difference.
As far as the Fermi bubbles go, if it is supernovae that powers them, you certainly are going to need more than one supernova. You're going to need a cluster of stars that explodes to produce enough energy to drive it out. But at this point, we don't have enough information from our Hubble data to observationally say what the total amount of energy is. That's a number we're aiming towards with our larger sample, but that would be able to tell the difference better between the supernova origin and the supermassive black hole origin.
Thank you. Other questions in the room?
Lisa Grossman from New Scientist, and this is for David. I was wondering if the results that you're getting for the Magellanic clouds tell us anything new about the hierarchical model of galaxy formation and growth in general, or do we not know yet, or just put it in a bigger context?
Yeah, I think what we're finding so far really hints that there is this rich field of debris in the periphery of the Large Magellanic Cloud, which is what you would expect to find from this hierarchical growth. And it's possible that it is stars being stripped off of the Small Magellanic Cloud or from other satellites that were disrupted earlier. And so once we analyze all of our data, I think we'll have a much better picture of what exactly is going on.
Okay, thank you. Another question?
David Aguilar, Center for Astrophysics. I have a question for Paul. 20 years ago, when we saw the Eagle Nebula, there was a lot of talk that today in real time it wouldn't exist because of the stellar activity and the large stars that were blasting everything away. I think I heard you allude to the fact that you do believe it still physically is there.
It's still physically there, as in...
Well, as if I could beam myself to it at this very moment, I'd see it. It hasn't been blown away by the stellar activity over the time period that we're photographing
because it's 2.5 kiloparsecs away. The rate of ablation that we calculated 20 years ago implied that there were the rate at which those pillars had formed, that the gas had been wiped away between the pillars, was probably measured in the 10 to the 5 to 10 to the 6 year kind of range. So, yeah, I think they're still, if you could transport yourself there right now, I think they'd still certainly be there. But thinner, because it's clear from this larger field of view that you can see certainly at the bottom of the pillars that they're tapering away.
Okay, thank you. Other questions in the room? Yes, this question over here.
Hi, Ethan Siegel. This is a question for Julianne. Hi, I'd like to know about the possibility of producing a 3D dust map of Andromeda to learn about the thickness of the dust from extinction and things like that, and also if you are discovering background galaxies that are behind Andromeda, and if so, can you tell us about them?
Yeah, so this morning I talked some about this, and it turns out that this was not... We thought we were going to do something with dust. We didn't know this was what we were going to do. If you look in the near-infrared, most of the stars that you see are red giant branch stars. And red giant branch stars have a very narrow range in color. So if you see some of the stars that are redder than that expected color, it's almost certainly dust. And so what we've done is we've taken the near-infrared equivalent of that optical image, broken it up into little 20 parsec on a side regions. And within each one, we actually fit for a model where it's stars that are in front of the dust and stars that are behind the dust. And so from that, we get not only the amount of dust that's in that 20 parsec region, but we also get the tomography of where is the dust with respect to the stars. And it turns out that the majority of that is not so much where the dust is relative to the midplane of the galaxy. It turns out a lot of that is projection effects, because M31 is highly inclined. So if you are looking from the side where it's tipping towards you, you see very few stars from the outer. When you look on the near side, you're looking in the outer galaxy, and when you look on the far side, you're looking at the inner galaxy. And so a large fraction of stars will be extincted. Whereas if you look on the far side, the stars that are in front come mostly from the inner galaxy, and the stars that are behind are the outer galaxy. In this case, it doesn't. And you can see this when you actually look at a map of Andromeda. It looks dusty on one side, and it doesn't look dusty on the other. And it's not that all the dust has migrated to half of the galaxy. It's just that geometric effect. So we can actually, and we have fit for that, and that allows you to model the three-dimensional distribution of stars and to figure out how thick that disk is. And the really nifty thing is that the disk of red giant branch stars is about as thick as the thick disk in the Milky Way. Whereas in the Milky Way, the thick disk is, 10, 15% of the stars, whereas in Andromeda, the majority of stars seem to be in this big fat disk. Now, as part of FAT, Raja Guhathakurta and Claire Dorman have been doing extensive Keck spectroscopy to measure kinematics of all these stars. So from the Hubble data, we know what kind of star it is. We measure the spectroscopy, and you can measure the kinematics. And the kinematics that Claire is measuring, which she's presenting, I think, on Thursday, is very consistent with this fat disk. Sorry, that was a long answer. Sorry.
Thank you. We have another question over here.
Govert Schilling, freelance from the Netherlands. I have a question for Andrew. I see how the spectroscopic observations can tell you about the radial velocities away from us and towards us. I'm not completely sure how you can translate that into outflow velocities. Is that because you know the angle in which they are moving with respect to the line of sight?
That's right. So in the observations that I showed you, where you're looking in a direction towards a quasar which is at a so-called galactic latitude of 10 degrees or so. In other words, we know how many degrees above the equator of our galaxy we're looking. So we can project what velocity does that translate into away from the galaxy in the direction straight up from the galactic center. So because we know the angles that we're looking at, we can calculate the direction that the outflow velocity is moving in.
Do we need to know the opening angle of the bubble?
Yes. So the opening angle of the base of the bubble, we actually have information on from X-ray data. And you can see that bicone in X-ray images, and that's how we constrain that. That's right.
Thank you. Any other questions in the room? Yep,
Hi, Dan Cleary from Science Magazine. Question for Daryl. You talked about the Sagittarius A star being in a quiescent state most of the time, and then you saw these couple of flares. Why is it in such a quiescent state? You know, it's a supermassive black hole. Shouldn't it be gobbling stuff up all the time?
That was the subject of my dissertation. I will not give you a lecture on that right now. So it turns out that actually a lot of galaxies tend to, well, we've slowly moved toward the, I think, realization that you don't have black holes that are on and black holes that are off in a permanent sort of way, that they're cyclical systems. And part of the reason people were very excited about this G2 potentially gas cloud event was that it might be an opportunity to see our own black hole switch from a quiescent to an active state. And this variability, we see variability ubiquitously in AGN when we look out into the universe. And so that was a very exciting prospect. But that, when I talk about it being quiescent or active, that's a continuous, much more massive flow of material through usually an accretion disk. In Sagittarius A star, the accretion disk is a little bit puffed up. It's not quite the same canonical flat accretion disk you would expect. But the flares are a little bit distinct from that. The flaring seems to be sort of a property of the inner regions of the disk, and they're very quick. They don't seem to be connected to this persistent flow or lack of a flow. So Sagittarius A star is a little bit of an outlier in our AGN models. It's a very, very quietly accreting system. There's not much mass available for the black hole to accrete at the moment. As Andrew has pointed out a few times, you know, we have a lot of evidence of past activity. Maybe that was supernovae. Maybe that was accretion of the supermassive black hole. There's some hints that even objects like this magnetar could have contributed to some of the past episodes that we've previously attributed to the black hole. But this cyclic behavior of black holes does seem to be a property of most of them. And the flaring, we don't get to study black holes in great detail all the time. So our black hole, Sagittarius A star, is close enough and massive enough that we can see these flaring events. For a lower mass system, like a stellar mass black hole, they'd probably be too fast. We're not even sure that they exist. We'd need sort of really, really, really fine timescales to see them. And for a black hole, for example, like the one that we think lives in Andromeda, we're pretty darn sure it's in there, the timescales are very long. So what you call a flare versus what you call a rise and a fall, it's a little difficult to parse the language. But this flaring phenomena is something we really uniquely see in Sagittarius A star. Whether that's selection or not, I think is open. But
okay, thank you. Anything from the web? Yep.
Okay, this question comes from Camille Carlisle at Sky and Telescope magazine. It's for Andrew Fox. How many AGN did you use in your analysis?
We have a total sample of about 20 AGN. At the moment, we put out the results on the first AGN, the one which was closest to the galactic center, where the X-rays are strongest. So that's the subject of our initial paper, but the follow-on work will look at the full sample of 20 or so.
Thank you. That's all we have from the web.
Okay. Any other questions in the room? If not, I would like to thank our speakers, Daryl Haggard, Andrew Fox, Paul Scowen, David Nidever, and Julianne Dalcanton. Now, before you all go, there are just a few announcements. The Hubble M16 Pillars of Creation image will be shown in large format and living color on the NASA Hyperwall in the exhibit hall as part of a special presentation at 4:30 p.m. today. So please be sure to be there. Also, there is an AIP press reception honoring the 2014 American Institute of Physics Science Communication Award winners. That is tomorrow from 5:30 until 6:30 p.m. In 309, which is the room in between this one and the press office. So please be sure to be there. Our next briefing will be tomorrow at 10:15 a.m. on exoplanets and host stars, part 2. Thank you very much to everyone. Thank you to everyone virtually, and we'll see you again tomorrow.